Hello, my name is Avrisham Eskandari, and today I'm going to be talking about the advancements in the study of the catalytic reduction of dinitrogen to ammonia and its advantages for the industrial world. This review is really focused on the article Catalytic Reduction of Dinitrogen to Ammonia at a Single Molybdenum Center, which is the article that I'll be really thoroughly discussing in this presentation. So, ammonia is actually a very useful compound. It's used in the industry in many fields, including the production of plastics, the production of fertilizers, cleaning agents, and explosive. The process actually takes nitrogen air and it reacts it with dihydrogen, and the dihydrogen is actually produced from natural gas, specifically methane, and the nitrogen and the hydrogen are reacted at very high temperature and very high pressure. As you can see, it's about 350 to 550 degrees Celsius and 150 to 350 ATMs. So as you can tell, this is a very energetically costly process. It really has its disadvantages. This process, as I said again, is very energetically expensive, and it's very environmentally costly due to its dependence on H2 gas. H2 gas is produced from methane, which is natural gas, and methane is produced by the burning of fossil fuels. So these fossil fuels are burnt. They also produce CO2. Both methane and CO2 are considered greenhouse gases, which absorb a lot of heat, which is why the temperature of the Earth has been going up and has been causing this phenomenon referred to as global warming. So therefore, as you can tell, it not only is it energetically expensive, but it's also not good for the environment. So there's other ways that ammonia is produced in the world. A fascinating way that's been studied a lot has been the production of NH3 from N2 by nitrogenase, which is an enzyme that's produced by certain bacteria in the and these bacteria are capable of nitrogen fixation, which is a process where they reduce the N2 to 2 equivalents of NH3 with the use of 6 protons and 6 electrons. And they're able to do this at 1 atm of ambient pressure and mild temperatures, which is very interesting compared to the pressure and temperature that's needed to carry out the Haber-Bosch process. It also does this with the use of one or more transition metal centers, which are either iron, molybdenum, or vanadium. The reduced product is then used by the bacteria itself or other organisms in a biosynthesis of macromolecules like amino acids and nucleic acids. So it's actually really interesting because if these enzymes exist in nature, it kind of creates this idea of would we be able to create a biological catalyst that would be able to reduce N2 to NH3 under these ambient pressures and ambient temperatures. So meaning a less energy intensive process, way less energy intensive process. It's important to note that nitrogen does really need to be converted to ammonia to be used in biosynthesis because N2 has a triple bond and is a very inert and unreactive compound. So the structure of nitrogenase has been extensively studied. The nitrogenase enzyme has, in fact, 2 proteins. There's the iron protein and the molybdenum iron protein. The iron protein contains a singular Fe4S4 cluster between its 2 identical subunits, and this cluster actually, its main function is to serve as the electron donor to the MOFE protein, which is where the catalytic reduction occurs. The MOFE protein has 2 cofactors, the FeMO cofactor and the P cluster cofactor. It's believed that the FeMO cofactor is the site of the reduction, and the P cluster cofactor is involved with the electron transfer from the Fe protein. So as you can see on the right here, this is a proposed structure for the FeMO cofactor cluster. The molybdenum right here is believed by many to be the site of the reduction of N2 to NH3. There are some studies who suggest that Fe in this cluster is actually the location where this catalytic reduction occurs. So as you can tell, the exact site of the reduction in the MOFE protein and the overall mechanism by which nitrogenase performs the reduction are still unknown. It's actually also important to note that there are some vanadium-based nitrogenases with vanadium replacing the molybdenum. So, the discovery of the first transition metal complex containing N2 ligands happened in 1996. Allen and Stenoff were actually the people who discovered it. And the complex that they were synthesized was nitrogenopentamine ruthenium 2 complex. And with the synthesis of this complex, the possibilities of creating non-biological catalysts that could reduce N2 to NH3 with the use of protons and electrons at ambient pressure and temperature with well understood and known transition sites became more and more realistic. So, really, there was the hope of creating something with capabilities of acting like nitrogenase. So, further, a development of the first abiological molybdenum-based catalyst occurred, which was the trans-MON2,2-DPPE, as you can see right here. So, and further from that, Chat et al. Synthesized metal complexes with molybdenum and tungsten centers and tertiary phosphine ligands. So, what was astounding about these compounds that Chet's group was able to come up with was how astoundingly reactive they were. So further on, since then, a lot of more N2 complexes have been discovered, but it's really interesting because only a very few of those have been able to catalytically convert N2 to NH3, and only fewer of them have even been able to had at least to a certain point been able to do that with mild temperatures and ambient pressures using mild reducing agents. And the mechanism of them was really never known. So Greco and Schrock were able to prepare MO complexes with triamidoamine ligands of ARNCH2CH23N, which is you can see right here. So what actually happened with that complex was that for some reason it was able to form a very stable and unreactive bimetallic complex by dimerizing. So they wanted to really deal with this issue. And in order to do this, they created this new ligand, which was the tetradentate HIPT N3N3- triamidoamine ligand, where HIPT N3N3- ligand is the HIPT portion is actually hexaisopropyl terphenyl. So what this actually did was this group was so large that it really maximized steric hindrance, and it also increased solubility relative to the previous complex, which was really desirable for these aqueous reactions. So this is the HIPT group right here in entirety. The circled portion is actually a group that, along with the same group on all these three HIPT ligands, creates this trigonal pocket which protects the dinitrogen binding site, therefore the dinitrogen as well as all its reduced products. So by doing this, by altering this catalyst ligand, what they were able to do was achieve successful catalytic conversion of dinitrogen to ammonia at ambient pressure and temperature on a sterically protected single molybdenum center. And this was very amazing because this was really done for the first time. So not only were Yandalov and Schrock able to create and synthesize this successful catalyst, but they also considered the mechanism by which it was performing its reducing functions. So they proposed a mechanism for which N2, where the nitrogen has an oxidation state of 0, would be reduced to NH3, where the nitrogen has an oxidation state of 3 minus. And the mechanism that they proposed was that there was actually, what was happening was an alternating transfer of 6 electrons and 6 protons. So as you can see, it goes proton, electron, proton, electron, proton, electron. So this first step is actually the one step that's kind of a bit different. What's believed to happen is that there is an initial protonation occurs on the amido nitrogen rather than the N2, and that is followed by a proton-coupled electron transfer reaction. So the proton source is actually 2,6-lutetium BAR4, and the electron source, or rather the reducing agent, is cobaltocene. So the addition of 1 equivalent of the proton source and 2 equivalents of the electron source of the reducing agents to the MON2 right here actually yielded a 100% yield of this compound right here, the MON double bonded to NH. And this was because there was an addition of pretty much 1 electron and 1 proton. So what they did next was they added 7 equivalents of the proton source and 8.2 equivalents of the reducing agent, assuming that the reaction would proceed all the way from here to here. The extra reducing agent is really used since this is this change from MONH3 to MON2 is also a reducing step. So what actually ended up happening was that they obtained MONH3 BAR4 at approximately 60%. So the reaction was really stopping right here, and this is what was isolated. And COCP2 doesn't reduce the compound to create this MONH3. So once the MONH3 plus was reacted with 3 equivalents of the reducing agent in benzene, 10% of this MONH3 plus was converted to the MON2. So since the reaction wasn't actually going all the way to the MONH3, what they realized was that there was a need for a stronger reducing agent, which is why they introduced decamethylchromazine, which is actually 0.13 volts stronger than COCP2. So there were actually a few other issues in the reaction. The formation of the MON2 from MONH3 in this reductive step right here was occurring on the minutes to hours time scale. So they really had to be careful to allow sufficient time for this conversion to occur in this cycle before the addition of any more proton or electron source in the following catalytic cycles. Another issue was that there was a rapid oxidation of the proton source, which was decreasing the efficiency with which N2 was being reduced to NH3. So in order to solve this problem, they allowed for the slow reaction between a proton source and the reducing agent relative to the MO species. What really needs to happen for gaining the greatest yield possible, it has to be the slow and controllable addition of the proton electron source to the MO species. So this table is actually depicting rates of production of NH3 as a result of the catalytic reduction of N2 at 23 degrees Celsius to 25 degrees Celsius and at 1 atm from different MO compounds that were seen at the scheme on the previous slides. So these were all compounds that were isolated, and they were run through this catalytic cycle with the addition of 36 equivalents of the CRCP2, as well as the addition of 48 equivalents of the proton source, or the lutetium BAR4. So as you can tell right here, I'm sorry, there is a different addition of equivalents of NH3 that were produced, and it varies very, very slightly. It's all approximately 8 equivalents of NH3 were produced from each compound. Each compound was actually run through the cycle a different amount of times, which is why this occurred, even though the same amount of the proton source and electron source were added. So as you can see, if we started with a compound earlier on in the cycle, it was run through the cycle more times because essentially all those protons and electrons would be used up early on in the cycle. So you need to run it through the cycle more times to obtain this 8 equivalents of the NH3. All of them pretty much presented a yield between 63 to 66%. So since the successful reduction of dinitrogen to ammonia at ambient temperature and pressure was achieved by Yandalov and Schrock, a lot more studies have been conducted to understand the mechanism of these reactions, where there is an alternating addition of protons and electrons, and there is a reduction of eventual reduction of N2 to NH3 as a result of this process. There's also been more studies into improving the catalytic conversion process, so meaning gaining higher yields and higher efficiencies. So firstly, from the intermediates proposed in the mechanism in the previous slides that was suggested by Schrock and Yandalov, actually 2 more intermediates have been definitively isolated, and that makes for a total of 8 intermediates that have now been isolated, and this really further just validates the mechanism, the suggested mechanism, and makes it so that it's more likely to be fairly accurate. So not only has the mechanism been further studies, but there's also been a continued interest in producing other such catalysts. In 2013, there was a synthesis of a successful molybdenum-based catalyst that reduced N2 to NH3. This complex, which is actually MON22PNP2N2, with PNP being 2,6-bis ditert-butyl phosphenomethylpyridine, which is quite the mouthful, produced actually up to 12 equivalents of ammonia based on each MO atom of the catalyst. And this was actually quite interesting because the catalyst that was made by Yandalov and Schrock in the 2003 paper actually only gave 8 yields per catalyst, where there was an expected theoretical yield of there should have been a theoretical yield of 12 equivalents. So again, this catalyst was actually a lot more efficient, had a lot higher of a yield, and it was also able to do its task under the desired ambient pressure and temperature. So as I've said before, a lot of goals of these studies are now to improve efficiency and yield. A lot of these catalysts that have been synthesized, these abiological catalysts, have an efficiency of between 63 to 66% versus the 75% for the FeMO nitrogenase. So again, the biological form of these catalysts is still quite a bit more efficient. So this can be really summarized by saying achieving a high yield catalyst that can reduce N2 to NH3 at ambient pressure and temperature with a well understood mechanism would provide a replacement for the Haber-Bosch process, which is both energetically expensive and environmentally costly. So not only is this Haber-Bosch process bad for the environment, it's just purely not sustainable. As the population is rising, the need for the use of fertilizers and for the, because that's correlated with the need for food and the need for cleaning agents and plastic products is going up. So therefore, the need for ammonia is going up and up, and this process is just simply not good for our planet because of the greenhouse gases that are produced as a byproduct. The temperature of the earth is rising, and the earth is getting hotter and hotter, which is the process of global warming. And despite efforts by certain politicians to deny climate change, it is actually a really real thing, and it is wiping out species and really changing the fate of the earth. And it is up to scientists to stop it and really prevent some sort of great natural disaster from occurring. This concludes the end of my presentation. I would like to thank Dr. Haitalu for a great semester and all the things that he has taught us in our class, and all the time investment he has put outside the class in helping us learn.